We're going to take a look at where the formula for law of sines comes from. So we are going to derive it, which means we're not proving. I don't have the law of sines. I'm showing actually where it comes from. All right. I'm going to use the triangle here, triangle ABC, but it's a generic triangle. It wouldn't matter how you orientated this triangle or if it um, were an obtuse triangle, right triangle, it really doesn't matter. Well, a right triangle we wouldn't really need the law of sines, right? But we have right triangle trig before you get to this point. But anyways, we could use any triangle. I just drew a generic one here. And here's the idea. So what we're going to do is draw this altitude. Remember, an altitude goes from one vertex and to the opposite side and at a right angle. Think of like height, right? If you were to talk about the height of, say, a plane flying overhead, you're talking about the altitude, the direct height from the ground at a right angle. You're not really measuring, say, from point A. Okay? So anyways, we need this altitude. And typically we call altitude h to represent height. Again, the height we measure at a perpendicular. Okay? So from here, now we really have two right triangles. Right? We have, change colors here. I mean, I know it's easy to see, but we have this one on the left. And if we call this point, I don't know, D, right? We have triangle ACD, a right triangle. But then we also have this one on the right, also a right triangle, triangle BCD. Okay. So one more thing to throw in here, which I should have started with, is common notation. If I call this angle A, the side opposite is little a, right? Common notation is capital letters represent angles, lowercase letters represent the lengths of the sides. So this is B, and this entire length down here is C. Okay. All right. So now looking at the left triangle, we're going to use sine for two reasons. One, like the um, property, the formula we're trying to get is called the law of sines, so that's why. But also because if we used cosine of A, I would use this adjacent side here, and I don't really have a variable for that, right? Like C is the entire length from AD and including DB here. So, all right, so we want sine A equals opposite with H over B. Right? But if I looked at the right triangle, I have sine B equals opposite over hypotenuse, H over A. All right, now what is in common with both of these is the fact that we're using that altitude H. So if I solve for H by multiplying by B, I multiply by B here, we'd have H equals B times sine A. But on the right hand, right, same process, I'm multiplying by A sine B equals H. But if H is equivalent to this and H is equivalent to this, then that means those two things are equivalent, right? H is expressed in two different ways. So therefore, B sine A equals A sine B. And from here, like, just an easier way to memorize it is we keep the letters together. So what we could do is divide both sides by the sides if you want. So let me rewrite this, because if you've used or have seen the law of sines, you know that there are two forms. So here's where each of the forms come from. On this side, I'm going to just divide by both sides by AB. Okay? I'm going to divide by the length of the sides. So the b's would cancel and I'd get sine A over little a, and here the a's would cancel, we'd get sine b over little b. Right? Or on the right hand side, if we divide by both trig, sine A, sine B, the sine identity, sine B, okay, and then simplify, we would have B over sine B, and then we would have A over sine A. Now, I showed that really we could have just said, right, we'll use this left side, and we know that we could do the reciprocals of both sides or cross multiply and divide, right? I know we could have easily used this to get here as well, but without relying on the first identity, we have the second one straight from the equation, but the actual formula includes one more thing, right? So either form, really, like what's most common is would use this side if we know, if we know the sides and we're trying to get the angles. Again, it doesn't matter, but that's most common because our unknowns we really like in the numerator, right? Just easier. But we usually use this side if we're trying to find an angle. And then we'll use this side if we're trying to find the side. Okay. But anyways, there is one more side, right? C. But the process would be the same. Okay, I only drew one altitude. So to get this piece, we would rely on either A or B. So often we just say similar to find this last one here. And of the other form too, right? If you did this form, we say similar for side C. And really quick, like why? Because I don't think it's like totally obvious, but if I were to redraw that triangle that we started with, but instead I chose to do, let's say, this altitude, called that H, right? Now I would be using the sine of A, opposite over hypotenuse, this is side C, and then I would use the angle C and do opposite over hypotenuse, and then right I would be missing this piece, but the result would be the same. I'm going to solve for H and find these identities where I get H represented by two different things, and then I'd have the last piece of the equation. All right, hope that helps. Some of these formulas aren't rocket science, right? Like we already knew right triangle trig. It's just a little trick of drawing that altitude for any triangle to derive the law of cosines.